hopefully we'll have enough time at the end, where after we've done conic sections in the first half and then the parametric and polar in the second half, our last lesson should be a lesson that pulls those two together. Because there are ways of doing conic section graphs as polar equations. So hopefully we'll have enough time that we can kind of end on that and pull it all together, which sort of gives reason to why it's all in one chapter. But it's going to feel like two very distinct parts at first, because we're going to really hit the conic sections, and then we'll take a quiz, and then it's going to feel like we totally went another direction. But hopefully we'll be able to come back to where you can see how it all ties together. Okay? So we talked a little bit before class, before break, about why they're called the conic sections. And it's this idea that if you take two conics and you put them one on top of the other with their vertices connecting, and then take a plane, depending on how you slice through those cones with that plane, gives you different shaped objects. So those different shapes give us the different conic sections. So if we go straight across, we get a circle. If we go across one cone but at more of a slant, then we get the ellipse, excuse me. If we just go through one cone but kind of slant it so that it's going through the base and then through a side, then we get this parabola shape where the intersection is. If we slice it more up and down and go through both cones, then we get this double parabola, which is called a hyperbola. So those are the four conic sections that most people think of when you say conic sections. Circles, parabolas, ellipses, and hyperbolas. But if you think about slicing through this double conic shape with a plane, there are some other options. And these are options where the plane actually goes through those vertices, where the 2 points meet. And when that happens, these conics are called degenerate conics, which I think is kind of a strange name for them because it kind of makes them sound like they're, robbing liquor stores or something. Degenerates. But it's not. Degenerate just means that the plane actually somehow goes through the point where the vertices meet. And so there's 3 different ways that can happen. One is if our plane goes straight across right here at that point, and so then the only intersection between the cones and the plane is a point. Another possibility is that our plane kind of sits along the side of the cones, going through this point where the vertices meet. And so because it's tangent up against this round cone, the intersection here really is just a line. Okay? And then the other possibility is our plane actually chops right in half, basically right down the middle, right through that point where the vertices meet. And so then you actually get 2 intersecting lines as the intersection between the cones and the plane. So based on this type of intersection, that means lines could actually be thought of as conic sections. And so that's actually what we're going to start with today. We're going to start by talking about lines, but as conic sections, from a conic section analytical geometry kind of point of view, which is different from what we've talked about lines in the past. This isn't just here's the equation and graph it, or here's the equation and solve it, or whatever, like we've done since you were in pre-alg. This is finding the inclination of a line. finding the angle between two lines, or finding the distance from a point to a line. So in a way, you could almost think of this as being a more geometric approach to lines than the more algebraic and graphical approach that we've done for many years in the past. Okay? Now, we're going to find that there's some connections to things that we already know how to do, but our point of view is just a little bit different. Okay, so these are the three things we want to be able to do by the end of class today. Be able to find an inclination for a line, be able to find the angle between two lines that have been graphed, and find the distance between a point and a line where the point's not on the line. Okay? All right, so let's start with inclination. So when we start talking about inclination, we're actually going to combine two things we know from previous experience. We're going to take what we know about lines, and in a sense, we're going to combine it with what we know about trig. Because when we talk about inclination of a line, what we're talking about is, what is this angle right here? So for every line other than a horizontal line, the line is going to have to cross the x-axis somewhere. So when it does, it's going to create an angle with the x-axis. Okay? And it's that angle that we're interested in. That angle is going to describe the inclination of our line. Now, if it's a vertical line, then that means our line is perpendicular to our x-axis, and so that's just going to be a pi over 2 radian or 90-degree inclination. If it's something other than vertical, then we need to be thinking again in terms of that idea of starting in standard position and rotating to get to a certain point, and that angle that's being made by the rotation. So if you imagine that this line had started here on the x-axis and then rotated into this position, what is that angle? That's what we're looking for. And notice here that it says our angle has to be a positive angle, so we have to be going counterclockwise in our rotation, and it's going to be an angle that's going to stay less than pi. Okay, so I'm not trying to rotate around to get down here. I'm trying to rotate to get to anything that's up here above the x-axis. Okay, so if it's a vertical line, we know it's going to be 90 degrees. Obviously, if it's slanted this way with a positive slope, then we're going to have some sort of acute angle. If it's slanted the other way with a negative slope, then we're going to have some sort of an obtuse angle that we're trying to find. Okay? But it's all about that angle being created by the line and the x-axis that stays less than pi. So any questions on what we're looking for? Does that make sense? All right, so how do we find it? Well, the first thing to realize is that there is a connection between inclination and slope. Right? Slope is a way of describing sort of the steepness of a line. Well, if I start talking about what this angle is, that also seems to kind of indicate just how steep my line is going to be. So there's a definite connection there. Okay, so if I, for a moment, imagine that I'm taking a particular point out here on this line. If I shift back into trig mode for a second, and I'm interested in what this angle is, probably what I would do is drop down a perpendicular, maybe. No. Oh, please don't lag today. There we go. A little perpendicular line there, create a little triangle and see what happens. Okay? Now, if I know what this point is, and then I've got this point here where the intersection takes place, how would you find slope?
Oh, you find the rise over like the length.
Yeah, so rise over run, which with points would be difference of y's over difference of x's, right? Okay. Well, if I take the difference of y's, what does the y value for that point have to be?
0.
0, because it's on the x-axis. So my y's are simply going to be whatever y2 is. And y2 really is just that distance right there. For the moment, I'm going to call it p. Okay? Now, what about x's? Well, I'm not sure what this x is, but if I subtract these two x's from each other, what I'm going to get is just that part right there. Right? So let's call that q for a second. So if I know from past experience that the way to find slope is to take the difference of y's over the difference of x's, and in this case, I've said the difference in the y's is this p-value, and the difference in the x's is this q distance right there. What else does p over q represent?
Tangent theta.
Tangent of theta. Because now in triangle speak, that angle means that's opposite and that's adjacent. Okay? So, we can use that. We can use the equation that the slope of my line is really just the same thing as the tangent of whatever that theta value is. And by being able to say that, since I can usually come up with slope from the equation of whatever the line is, I should then be able to come up with what theta is, because it's just going to be the inverse tangent of that slope. Everybody following me? So slope and tangent of theta are the same thing. That allows us to set up an equation which we can then use to help us find inclination. Because we usually know what the equation of the line is. So if I can find slope from the equation, then I can find the theta using this equation.
So you would do inverse tan if you know the slope?
Exactly. Make sense? All right, let's try one. So if I want to find the inclination of x minus y equals 2, it's not really part of the problem per se, but I would really recommend that the first thing you do, one of the first things you do, is actually graph this. Get some idea of what your line looks like, so you have some idea of what kind of angle you're looking for. Okay? So if I want to graph this, what do we often do first? So in this case, we could just go with x and y intercepts, right? That'd be pretty easy. What's another common step that a lot of people take?
Put it in slope intercept.
Put it in slope-intercept form. I'm going to recommend you put it in slope-intercept form because we're looking for the slope anyway. So if I put in slope-intercept form, 1, it's going to help me graph, and 2, I'll already have the slope, which will help me with my next step. So what is this in slope-intercept form?
Going to the x minus 2.
Everybody good with that? Okay. All right, so that means in terms of my graph, -2 is going to be about right there. And then my slope is what?
1.
1. So if I put a few points in here for a slope of 1. Now, again, this doesn't have to be perfect, so you don't necessarily need a graph to do this. Just put some axes off to the side and do a quick sketch. Okay? Because the graph itself is not part of the problem. The graph is simply to help us have an idea of what we're looking for. So in this case, what I'm looking for is right here. That angle that's being created by the line and the x-axis. And again, it's the one that would be rotating from standard position, which would mean starting at the x-axis and rotating counterclockwise to get there. Okay? So right now, I have a pretty good idea that this should be acute. So I should be getting an answer that's an acute angle. If I'm not, I've done something wrong. Okay? So now to actually find it, what's my slope?
1
1.
So what's my theta?
4.
In radians, pi over 4. In degrees?
45 degrees.
How'd Jonathan get that so quick? I didn't even see him push any buttons. He doesn't even have a calculator out.
Worked it out already.
Unit circle, right? So if you get to a point where your tangent of theta is equal to something that it should be equal to on a unit circle, I want exact answers. Now, whether it's radians or degrees is going to depend on your directions and on your context. If it's an application problem, a lot of times degrees is the better answer because applications are generally done in degrees. Okay? But you need to use either the directions for that section or the context of the problem to decide which one's better. Now, if you end up at a place where tangent of theta is equal to something that's not from the unit circle, then get out your calculator, do an inverse tangent, and give me a rounded off decimal. Okay? But whenever you can, I want exact. And that means when it's something off of the unit circle. Okay? So that's it. The inclination of this line is 45 degrees, or pi over 4 radians. That's your answer. That's what we're looking for. Questions? Okay, try right here. they got it? Anybody?
Are you asking us?
Does anybody think they've got it? Yeah, I'm pretty sure that's a question. What do you think?
That would have to be.
Shouldn't it be positive?
That would be degrees,
Shouldn't it
not
be-
radians.
what is
And
degrees?
it has to be positive, like you said.
Because if it's going down, it should be up 2, so it should be the other.
So other possibilities? Other suggestions?
146.3. So it's the inverse of that.
Yeah. For radians, I believe.
Anybody else?
2
Got something other than those two?
I think I have that answer in radians.
What do you have in radians?
2.55.
Anybody else?
Could be wrong.
Alright, let's check it out. So, what should we do first? Okay, so what's it going to be in slope-intercept form?
Yeah.
Plus what? 2? Okay, everybody agree with that? Slope-intercept form? Alright, so in terms of graphing then, that means I'm at a positive 2. I can go down to over 3, down to over 3, or I can go up to left 3, up to left 3. So I've got a line that looks something like this. Which means if this is the angle I'm looking for, what kind of an angle is it going to have to be? Obtuse. And really that again comes down to our slope. If I have a positive slope, then the inclination is going to be doing something like this, and so I should always be getting an acute angle from that. But if I have a negative slope, then the inclination is going to do something like this, and that should always give me an obtuse angle. Okay? So when I set up my equation of negative 2/3 being equal to the tangent of theta, if you simply punch in inverse tangent of negative 2/3, what does the calculator tell you? It gives you the negative 33.7. Okay? But this is where we can't just rely on the calculator again. We have to use our brains along with it. Because the first issue is, as someone mentioned as we put it up here, the directions said, the definitions said, that inclination has to be a positive angle. So a negative 33.7, although it's what the calculator gave me, should not be my final answer. Okay? So why did it give me negative 33.7 if that's not the answer I want?
Because that's the other angle.
The complement?
Because tangent is, or tangent -1 is from negative pi/2 to pi/2.
Bingo.
Right.
Remember when we talked about inverse trig functions?
Yes.
And in order to keep it a function, we had to limit the range. So we had to limit which quadrants our angles could be in. So your calculator only knows how to deal with functions. So when you type in inverse tangent of negative 2/3, it's only going to give you an answer that's either in the fourth quadrant as negative or the first quadrant, because those are the two quadrants that tangent is allowed to, inverse tangent is allowed to give you an answer in. But what we really want is something that in essence is a second quadrant angle. So we then have to use what the calculator tells us and make it work for what we're actually talking about. Okay, the calculator is not going to give us the 146.3 because it's not within that restricted range that we're allowed for an inverse tangent function. So what that means is I went negative here, the 33.7 degrees, which then means that the vertical angle across from it, if it would draw, there we go, would also have to be a measurement of 33.7 degrees. Which means the angle I want then has to be 180 minus that 33.7 degrees to get the green part I want, which is the 146.3. Okay? Now, if this had been a positive slope to start with, then we would have been talking about an acute angle for our inclination. And when I punch the buttons in for inverse tangent, the answer I get is the answer I want. It's going to be a first quadrant acute answer, end of story. But when it's negative slopes, meaning we're going to be talking about obtuse angles for the inclination, then you have to do this extra step and subtract what the calculator tells you from that 180 to get what we really want. So again, that's why it's good to just do a quick little sketch off to the side, draw yourself some axes, kind of sketch in what your graph's going to look like, so you know for sure if the answer you're getting here makes sense with what you really want. If I want an obtuse angle, a negative 33.7 doesn't make any sense. Okay? And if you think about 2.55 radians, this is 3.14, right? So does that make sense that that would be about 2.55?
Yeah.
Probably, yep. So that's probably the correct radian measure as well.
Okay, keep going.
Mhm.
If you find something in the second quadrant, can't you use inverse cosine then? Like, could you already have tangent?
Inverse cosine will give me a second quadrant answer, but my formula is all based on tangent.
So you can't do.
I mean, I guess you could, but it probably actually end up making more work. Right? Because if you just do cosine on the negative 33.7, you're going to get the answer to what the cosine of this angle is, not this angle. You see what I mean?
I'm talking about like, because you have like negative 2/3 is tangent, then you can draw like a triangle and then use the Pythagorean theorem to find out the cosine of it.
You already did more work than 180 minus 33.7 is. So could you, like, yeah, you could probably get there, but it sounds like way more work than just taking it from 180.
Some nice pictures on the same graph.
Yeah.
Yeah.
Very scenic.
Through the mountains, under the tunnels. All right. Is everybody okay with that? Figuring out inclination? All right, angle between two lines. So I'm given two equations for two lines. I want to know what the angle between them is. So when two lines cross, intersect each other, as long as they're not perpendicular to each other, you are going to get two pairs of congruent angles, right? The vertical angles across from each other. One pair is going to be acute, and one pair is going to be obtuse. Because again, we're stating that this is for non-perpendicular lines. If they're perpendicular, they're all 90. Okay? So if they're non-perpendicular lines, they're going to intersect in a way that's going to create one pair of acute angles and one pair of obtuse angles. And when we're being asked to find the angle between two lines, the assumption is that we're interested in the acute angle. Okay, that's always what we're referring to, is the smaller of the two, which is going to be the acute angle. So, if we know what the inclinations are of the two separate lines, then the inclination between, or the angle between the two lines is actually pretty easy. It's just the difference. Okay, that's what this says. Of course, it's saying it in mathematical speak, so it's a little bit wordy. But if we have the two inclinations, which you're calling theta 1 and theta 2 for the two different lines, and one of them is smaller than the other one, and the difference of the two stays less than 90 degrees, because we're looking for the acute, right? So if all of those things happen, then we can say the theta, which represents the actual angle between the two lines, is simply the difference of the two inclinations of the lines. So graphically, this is what we're saying. Whatever this inclination is, minus whatever this inclination is, because that one's obviously bigger, is going to give me whatever that angle between the two lines is. Okay? Pretty simple, right? The only problem is we're not usually given the inclinations of the lines. We're usually given equations for the lines, which we can find slope for. So yes, we could go through the work to find the inclinations and then subtract the two to get the angle I'm interested in. But if I could shortcut that a little bit, that'd be really nice. And we can. So the shortcut basically comes from taking the tangent of both sides of our equation we just said back here. Because we just got done saying this theta I'm interested in is simply the difference of these two inclinations, right? So if I take the tangent of both sides, that should still be equivalent, right? Just like squaring both sides, just like adding 5 to both sides. If I tan both sides, it's still an equation. They're still equivalent to each other. Okay? So using that idea for a second, we're going to take this tangent of theta 2 minus theta 1, and we're going to go back to everyone's favorite topic, trig identities. That's what this is. Okay? This is the trig identity for when we have the tangent of a difference. That's where this is coming from. It's not magic. It's nothing mystical. Okay? It's just the identity. So we're taking the tangent of theta 2 minus the tangent of theta 1, and then over that is 1 plus the tangent of theta 1 times the tangent of theta 2. Okay? Now, that doesn't look like we made things easier, but we actually did. Because based on what we were just talking about now, tangent of the inclination of line number 2 is the same as what? The slope of line number 2.
Oh,
And the tangent of the inclination of line number 1 is the same as the slope of line number 1. And we can fill it in here, and we can fill it in here. So what we actually end up with now, maybe, here's where I need the magic, is just to make this work. Oh, come on. There we go.
Too far.
Yeah, now it's like, oh yeah, let me catch up. There we go. Okay. So what we actually end up with now is this formula that says the tangent of theta, which now theta represents the angle between the two lines, is going to be equal to, and just to make it even a little easier, we're going to take the absolute value of the slope of line 1 minus the slope of line 2 all over 1 plus slope 1 times slope 2. And the reason absolute value makes it even easier is because now I don't even actually have to care about which one had the greater inclination in the first place to subtract them. Because with absolute value, it's not going to matter. So I can put my slopes in whatever order I want to, and it's going to come out okay because ultimately I'm going to take the absolute value of it to make it all positive. And then I take the inverse tangent of it and I'll get my theta. So because we normally get equations to these lines, which we can then find out slopes to these lines, this now becomes a very useful formula for finding out what theta is. Because if I substitute all my slopes in, work that out, then all I have to do is take the inverse tangent of that, and I've got my theta.
So when we don't know the inclination, we can just use the slope and plug it into that.
Yep. And again, it's not magic. It came from the identity for the tangent of differences, and it came from what we were just talking about, knowing that tangent of a theta and the slope of the line are equivalent. Okay? So let's try that. So the two lines I want to find the angle between are represented by the equations 2x minus y equals 4 and 3x plus 4y equals 12. So what are we going to need to do first, probably? Yeah, because again, we're going to need the slopes, right? And it's still a good idea to give yourself a little sketch. Okay, so slope-intercept form for 2x minus y equals 4.
Y equals 2x.
Okay, and slope-intercept for 3x plus 4y equals 12.
Y equals negative 3/4.
Say again.
Y equals negative 3/4 x equals 3.
Okay, does everybody agree with that? All right, so I'm going to draw these up here quick just so we can see what we're dealing with. So negative 4, slope of 2. So kind of like that. And positive 3, negative 3/4. Something like that. Okay, now it's not real easy to tell which one actually is smaller. But that's okay, because the formula is already set up now to tell us. Kind of looks like it's this one right here. That one looks a little bit smaller than that one does. Okay? All right, so now to actually tell that angle, I'm going to call this one slope of line 2, which is what? 2. And I'm going to call this one the slope of line 1, which is what? Negative 3/4. Okay? So, tangent of theta equals absolute value of what? What's going to go on the top? 2
plus
because it's minus negative 3/4, so the minus and the negative are going to become plus. Let me get that. Right? And then in the denominator, plus, because if it's minus on top, it's plus on the bottom. 2 times negative 3/4. I'm going to write it all out this way. But I did hear someone say, well, that negative 3/4 is actually going to change it back into a minus again, and you're right. Okay, but just to see where all the numbers fit in, I'm going to leave the minus with the 3/4 for a second. Okay, so slope 2 minus slope 1, 1 plus slope 2 times slope 1. All right, so now it's just simplifying. And we do need to get this simplified as much as possible so we can then take inverse tangent of it. Okay, so, let's take that to black actually. 2 plus 3/4.
11/4.
Yeah, and you're going to want to change it into an improper fraction because ultimately we're going to need to take numerator divided by denominator, so having it in fractions makes that easier. So 11/4 in my numerator. Denominator,
Over 1 minus 6/4, which is negative 2/4.
Negative 1/2.
Or negative 2/4.
okay. So 2 times negative 3/4, 2's cancel, that's going to be negative 3/2. Negative 3/2 plus 1, negative 1/2.
Negative 2/4.
And then if I invert and multiply, do I need the fourths when I multiply and divide?
It helps.
Actually, it doesn't, because it keeps the numbers bigger, and that potentially could make things more complicated than it needs
But
to.
then you can just cancel out 4s.
I can also cancel out a 2 from the 4. Okay, so I'm basically taking 11/4 now times
Negative 2.
the negative 2 over 1. So that's going to cancel, and I end up with a negative
11/2.
11/2.
Absolute value of negative 11/2.
But because all that's in the absolute value, I'm really talking about
11/2.
positive 11/2.
Tangent. Or 10 negative 1.
Is 11/2 one of the unit circle
Always
numbers? No. So grab your calculators, punch it in.
Theta in radians is 1.3909.
Okay, anybody got it in degrees?
79.6.
79 point what?
It's absolute value.
Okay, and so we're starting to see a little bit why it's a little bit tough to tell which one is actually smaller, because one of the angles is practically 80, so that means the other one's 100. Right? And when you start talking about degrees, like that's not a big difference. So pretty sure this is the one we want, and it seems to be almost 80 degrees. That's what we're looking for. Okay, questions about that? All right, last part. Distance from a point to a line, assuming the point is not on the line. So when we're talking about this again, there's a certain assumption we need to make, and that assumption is that if you drew a segment from the point to the line, that the segment would be perpendicular to your line. That's the distance we're looking for. So it's not just any distance from the point to the line, it's the shortest distance, which means your segment here that represents the distance would be perpendicular to the line that you're interested in. Okay. This one is just a flat out formula. I'm not going to derive it for you. I'm not going to show you where it comes from because it's a bit complicated. So this one is one of those that you just have to trust me. Okay. What you do need to understand about this formula, though, is where all of the pieces are coming from, because it's kind of a weird little formula. Okay, so write it down first. Make sure you got it down, and then I'll explain where it's coming from. So it's D equals absolute value, which is only in the numerator this time. It is not like this one where we had the absolute value of everything. Okay, angle between two lines, we take absolute value of everything. But when we're talking about the distance from a point to a line, the absolute value is only in the numerator. Make sure you keep that straight on your paper and in your head. So absolute value of a x sub 1 plus b y sub 1 plus c. That's your numerator, absolute value of all that. Your denominator is the square root of a squared plus b squared. All right, so where's all those pieces coming from? Well, obviously you have a point, and so the x1 and y1 are the coordinates of the point. So this right here and this right here are coming from these. You know what? Let me get it this way. Maybe this will be nicer. All right, so x1 right there. y1 right there. Okay? Then a, b, and c. Those come from the equation of the line. But notice the form of this equation. This is also called standard form, but it's the standard form where everything gets pulled over to one side and you set it equal to 0 on the other side. So it's more like quadratic standard form, right? Where we pull everything to one side and make it equal to 0. Well, you can do that with linears also. We just usually keep the constant over on the other side. But for this case, we need to write the standard form in this way so that we're sure we're using the correct a, b, and c values with the correct sign on them, positive or negative. Okay, so it's the a coefficient here that is our a here. It's the b coefficient there that is our b here. And it's the c constant there that gives us the c there. So in essence, your numerator comes from substituting the x, y ordered pair from your point into the equation and taking the absolute value of it. That's basically what you're doing. Does that make sense to everybody? Okay. And then our denominator is the square root of the a squared and the b squared. So again, same coefficient a and b is being used in the denominator. Okay? All right. So, if I have a line represented by the equation y equals 2x plus 1, and a point not on that line, which has the ordered pair 4, 1, I want to know the distance from the point to the line, and we're talking about that distance right there, where the segment would be perpendicular from the point to the line. Okay? So what should I do first?
Move the y over to the right side.
Yep. I need to get my equation for my line in the correct form, which means 0 on one side and everything else on the other side. So if I subtract the y over, and then I would really recommend when you do this, make sure you're putting it in x term, y term constant order, so then you're not picking the wrong a's and b's and c's when you go to put it into the formula. Okay? All right, so then for our equation, so the distance is going to equal absolute value of the numerator, which is going to be the 2 from my x term times the 4 from my x coordinate plus, what's b? Negative 1 from the equation times the 1 for my y coordinate. And then I'm going to add to that the 1. That's my c value, my constant. Okay? And then in the denominator, I'm going to take the square root, maybe. It's showing up there. Come on, there we go. Of, what about the square root of?
2 squared plus negative 1 squared. Wait,
So that's the a value, that's the b value, that's what's getting squared down here. Okay, so now again it's just simplifying. So what's my numerator going to be?
8.
An 8. Because we got 8 minus 1 plus 1, absolute value of that, that's 8. What's my denominator going to be? Square root of 5. Don't I leave my answer that way?
No.
Good. What do I want my answer to be?
8 root 5 over 5.
Yeah.
Now, if it's a problem like this, which is a straightforward, here's a point, here's a line, what's the distance? I want exact answers. This is what I would want. Okay? If, on the other hand, you are going through this process as part of some application problem, like maybe this point represents Johnny's house, and the line represents the road, and you want to know how far away from Johnny's house is the road, right? Then this probably doesn't make a whole lot of sense. If you go to someone and say, hey, I found out Johnny's house is 8 root 5 divided by 5 miles away from the road, they're going to go, what? So in an application kind of setting, you can go ahead and estimate it, make it a decimal. And so if this was that kind of problem where this is Johnny's house and that's the road, how far is Johnny's house from the road? How much?
3.5.
About 3.5. Okay? So it just depends on what the context is that you're doing this. If it's just a flat out, here's the equation of the line, here's the point, find the distance, I want exact answers. That's a more theoretical kind of problem. But if the line actually represents something and the point actually represents something and you're trying to find the distance in a more application, real life context, then making it a decimal approximation is fine because it makes a little more sense. Okay? Questions? Those are the 3 parts. Any questions on any of those? Inclination, angle between 2 lines, or distance from a point to a line?
Still not clear if we are supposed to put our answers in radians or
It's going to depend on instructions and context.
okay.
So if the instructions say one or the other, obviously go with the instructions. If they don't say, I'll take either.
Okay.
Okay? If the context is a real life problem kind of thing, and they're asking you like, you know, what's the angle inside of a triangle? Well, we normally talk about that in terms of degrees, so I'd expect a degree answer. Okay? So on the homework, there's a little bit bigger, that doesn't make sense. A few more problems than usual, because there's 22 problems. But the first 6 or so are like, here's the angle. What's the slope? Here's the slope. What's the angle? Like, that should take you all of 30 seconds, right? So I don't think time-wise it should be a whole lot worse than usual. It's just a little bit more than usual if you go by number of problems. The first few problems are pretty straightforward, very much like what we did here, where there's an inclination problem, and then there's a set of angle between lines problems, and then there's a set of distance from point to line problems. But then the last few problems, you're going to have to work these in combination. So you're going to have to use different things to find what they're asking you for. Okay, so be ready for that in those last few problems. You kind of have to use them in combination. You've got about 5 minutes. I do have the textbook loaded on Canvas now for chapter 10. So if you want to take a minute and just kind of peruse what the problems are, and if any of them look totally bizarre to you, you've got a chance that you could ask about it quick before you leave. And then all of this will be due for Thursday. Okay, so I want you to take a look at those quick and see if anything looks extremely bizarre.
Our state